Hello everyone, and welcome to this video on section 7.2. Now this is part one of this section 7.2 video series. I'm going to be taking you through a preview version of a Newton-Alta assignment for section 7.2. It's called the Calculus of Parametric Equations, and I'm going specifically over the objective heading derivatives of parametric equations in this video. All right, so please understand that questions I see in this video may not be exactly the same as the questions that you see when you work on the assignment yourself. But I'm hoping that the questions are similar enough so that watching me do them here will help you when you work on them on your own. All right. So here's what the assignment looks like in Newton-Alta's site. Upper left-hand corner, you'll see the title. Now again, you won't have the word preview. Upper right-hand corner, you should be seeing the mastery bar, which shows you how far along in the assignment you've gotten. But like I said earlier, I'm not going to be completing the entire assignment. If I look at the activity log here, I'm just going to be working on this heading called derivatives of parametric equations. All right, so these three sub-objectives. And then I'll put out a video, a part two, where I go over integrals involving parametric equations. All right, so we're just doing these three today. Now on your main page, you see a current objective, and beneath that, a question related to that objective. And at the bottom of every question, you should see a feedback button. All right, if you have any issues with the questions, you see typographical errors, or maybe there's some problems with the answer explanations, you can send feedback directly to Newton, and hopefully someone from their support staff will get back to you soon and help you resolve your issue. You will not have this instructor cheat button, right? This will not be there. But you should be seeing a more instruction button. All right, so if you're ever struggling with a topic or an objective or a question, click on this and you'll be taken to a page with further reading to do or videos to watch or both. And then you'll be given questions related to that instruction. And you can work on those questions with the instruction still available. You can keep referring back to it, and hopefully that makes getting through the assignment a little easier. All right. So first objective I'm looking at here, find the second derivative of a parametric curve. So remember second derivative from calculus 1. The value of the second derivative, right? They had this, d2y, d squared y over dx squared, right? The second derivative of y with respect to x. Remember, this gives us concavity of a curve, right? Is it concave up or concave down? So I'll write this up. How do we find this second derivative of point on a curve when we're given parametric equations? Now, before I get to the second derivative, of course, I should talk about the first derivative. So if we're given parametric equations, right, x of t, right, tells me the x coordinate for some parameter t, right, x depends on t somehow. And then the y coordinate also depends on this parameter called t. Right, that's the y coordinate. The first derivative, which remember what first derivative, dy over dx, right? Remember what this tells us is the slope of the tangent line to a curve. And So given parametric equations, this is pretty easy to find. The derivative of y with respect to x at any point, you know, for any value of t will be equal to the derivative of y with respect to t divided by the derivative of x with respect to t. All right, it's almost as if you're dividing the top and bottom by dt, even though that's technically not what's happening. And there we go. And again, this is sometimes referred to as y prime, right? You can call it, remember we did this a lot in Calc 1, dy over dx, y prime, slope of a tangent line. But yeah, this here is what we're going to be doing to find the first derivative of some function, some curve, slope of the tangent line to a curve at any given value of t. And then, of course, if we know the slope of the tangent line and we know the point that we're at, we could, of course, be able to write the equation of the tangent line. And then using this same concept, we can find the second derivative of a curve at any point. Now, the second derivative, remember, is d squared y, right? The change in y over the change in x squared, right? dx squared, which we could also call, y double prime. Remember, this gave us the concavity at a point, right? Was a curve concave up or concave down, right? Curling up or curling down at a point. And you might recall again from calculus 1 that if a point had a positive concavity, if the second derivative was positive, we were concave up, right? Y double prime positive for curves concave up. And if the concavity was, down, that meant the value of the second derivative was negative. And where curves changed from concave up to down or down to up, those were called points of inflection, right? Where the second derivative would be equal to 0. Well, the second derivative of y, right, with respect to x, what we're going to do is we're going to think of, and you can always think of it this way, the second derivative of y with respect to x, well, that's just the first derivative of y prime with respect to x, right? It would be y prime prime. And then I calculate this first derivative of y prime with respect to x the same way we did up here. Y prime, when we find y prime, when we find dy dx, it'll be something involving t. So then I take the derivative of y prime with respect to t in the numerator here. And then we're over dx, and again, just like earlier, take the derivative with respect to x. The derivative of x with respect to t in the denominator. So this here is how we're going to go about finding the second derivative and thus the concavity of some curve, of a parametric curve at some value of t. So for example, and I'll keep writing these up, and I'll keep writing these up. Now the first set of parametric equations we're given x of t is 4 times the sine of 2t, and y of t, y depends on t this way, it's negative 6 times the cosine of 2t. All right, so you may recall from the section 7.1.1 videos, when I eliminate the parameter here, I would get an ellipse, and we'd have x squared over 16, because x over 4 would be sine, and then square that, and plus y over 6 or negative y, and y over negative 6, that'll be y squared. When I square that, that'll be y squared over 36. That should be equal to 1. It's like sine squared 2t plus cosine squared 2t equals 1. We're going to see the graph of an ellipse here when I put this up, and I'll put it up in Desmos. All right. Now, if I wanted the first derivative, the slope of the tangent line at any point, for any value of t. Remember, every value of t takes me to a different point on this curve. So again, that's, dy over dx, right? The slope of the tangent line, change in y over change in x. So again, this is, you're going to do dy dt, right? It's basically kind of divide the numerator and denominator here by dt over dx dt. Right, so the derivative of y with respect to t in the numerator, which you might just call, y prime of t, and then divided by, dx dt, which you could call x prime of t, right? Whatever. So y prime, all right, dy dx, y prime is, of x, y prime, dy dx, y derivative of y with respect to x, the slope of the tangent line anywhere is y prime at t. Now y of t is this, right? So y prime with respect to t would be, the derivative of negative 6 cosine 2t. That'd be 12 times the sine of 2t. Using chain rule and all that. So it's 12 sine of 2t divided by, and then dx dt, the derivative of x with respect to t, so x prime of t. Well, if x is 4 sine 2t, then x prime with respect to t is, 8 cosine 2t. Put that down here. 8 cosine 2t. And I could simplify this to, this is 3 times 4, this is 2 times 4. So 3 halves, and then sine over cosine of something is tangent of that thing, right? So 3 halves times the tangent of 2t. So this describes for me y prime, dy dx. This tells me how to calculate the slope of the tangent line to any point on this ellipse. Now again, I'll put all the graphs up in Desmos in a second, but now they want the second derivative though. So again, that's, d squared y over dx squared, right? The second derivative of y with respect to x, which once again, we're going to think of this as the first derivative of y prime with respect to x. And then just like how we found the first derivative of y with respect to x, right, dividing by dt, right, all that, we're taking derivatives with respect to t. Doing the same thing here, the first derivative of y prime with respect to x, calculated the same way. I'm going to take the derivative of y prime with respect to t, and then divide this by the derivative of x with respect to t. And we simplify. Now, y prime we saw from the line here. Y prime in terms of t is 3 halves times the tangent of 2t. All right, so this numerator, the derivative of 3 halves times the tangent of 2t, well, that would be 3 times secant squared of 2t, right, the derivative of y prime with respect to t. And then the denominator here is the same as up here. It's just the derivative of x with respect to t. So that 8 cosine 2t, right, this up here, divided by 8, cosine 2t, which 1 over cosine is the same as secant. So this is 3/8, times secant cubed of 2t. And that's what they want right here. A little formula to describe to us the second derivative at any point, as long as we know the value of t that takes us to that point. Let's look at some graphs here. So I did this in section 7.1 video, to graph equations in parametric form, right? Parametric curves. You have to enter them like ordered pairs. So parentheses, and then how does x depend on t? It's 4 times the sine of 2t, right? And again, make sure you're in radian mode here. And then y was -6 times the cosine of 2t, right? And remember I said this is going to be an ellipse. And to have this go all the way around, sine 2t, cosine 2t, those both have a period of pi. So from 0 to pi should take me through the entire graph. And there you go. Here's this ellipse that I mentioned. All right. And let's go to a particular point. So I'm just going to copy and paste this here. And then just put in a value of t. All right, let's put in a value of t. So let's just go to a particular point. How about when t, I'll just replace t with, I don't know, pi over 6. And then for the, oh, come on, bring that back. And then for the y coordinate, same thing. I'm just going to replace t here with pi over 6, right? So there's the point when t is pi over 6, and let me label this, right? So you see this point here, this purple point on the green ellipse. Now, if you were to imagine a tangent line there, could have a positive slope. And let me show you that, right? Remember on my paper, the first derivative was this. All right, this was y prime right here, 3/2 times the tangent of 2t. If I plug in pi over 6, we should get a nice positive number. All right, I'll take that, 3/2 times the tangent of 2 times, and then t is, pi over 6 here, right? And you see the positive value come up, 2.59. So there's the slope of the tangent line at this point, and we can find the equation for it, but we're not asked to do that here. But yeah, if you were to imagine a tangent line at this purple point, right, it would have a positive slope, and then right here is that slope, 2.598 something. Also, look at the curve, right, at this purple point. It's definitely, the curve is definitely concave up here, right? It's curling upward. So if I go in and plug in, this is when t equals pi over 6. If I plugged in pi over 6 to our second derivative expression, right, that was this, the 3/8 secant cubed of 2t, could be a positive value. Right? We're concave up when t is pi over 6, right? So I'll do that here. 3/8 times, secant cubed of, and then 2 times pi over 6, I'm just going to put pi over 3. Oh, I guess I got to put that inside the third power. All right, so 2 times, so secant of pi over 3, and then raise that to the third power on each side. There. And yeah, so see how that's positive? When t is pi over 6, I'm at this point, got a positive slope, positive first derivative, and a positive second derivative, right, concave up. So it's positive tangent line, positive slope tangent line, and concave up as we're seeing. All right, but I could use this expression though, right? This expression here for the first derivative, this expression here for the second derivative, and tell you what direction the curve is pointing in at any value of t, and also if it's concave up or down at any value of t. But they just want the value of they just want the expression with t here. That's 3/8 times secant cubed of 2t. So back in the assignment. So 3/8 the second derivative d squared y over dx squared times secant I hope it takes this. Secant cubed of 2t. And if it doesn't take it, I'll have to put the power of 3 outside this. Yeah, so it took it. Okay. All right, so they wrote secant cubed is 1 over cosine cubed, but it's the same thing. As long as what you have is equivalent to what the correct answer, they should give it to you. All right, and then after every question, right, there should be some sort of answer explanation. Please look through these. If you're right, look through it just to make sure you're right for the right reasons. And if you're wrong, definitely look through it. See if you can figure out where you went wrong, right? Why you were wrong. And yeah, hopefully you can learn from your mistakes for future questions. Great. All right, so here we are again, another question on find the second derivative depending on t, right, for a parametric curve. So we'll have this d squared y over dx squared, right, the second derivative of y with respect to x, the concavity of the curve, but have it depend on the parameter t. So very similar to the last example with all these ways I was calculating it here. All right, so this time x depends on t this way. It's 5 times e to the 5t power. And then the y coordinate, depends on t this way. It's 4 times e to the negative t. All right. So again, first derivative, dy dx, the slope, for slopes of tangent lines, doing the derivative of y with respect to t divided by, and then the derivative of x with respect to t. All right, so the derivative of y with respect to t would be negative 4 e to the negative t divided by, and then the derivative of x with respect to t would be 25 e to the 5t. And of course, if I actually divide this would be negative 4 25ths, and then e to something over e to something, you subtract those powers times e to the negative 6t, right, negative t minus 5t. So this expression here would tell me the slope of the tangent line at any point on the curve described by these equations, but I need to know the value of t at that point. Okay, and then the second derivative, right? The second derivative of y with respect to x, the concavity of the curve at any moment. Again, this is just the first derivative of the first derivative, right? If I call this y prime in terms of t, it's the derivative of y prime with respect to x, which just like our first derivative here, the derivative of y prime with respect to x, I'm taking the derivative of y prime with respect to t and dividing that by the derivative of x again with respect to t. All right, so the numerator, here's y prime. The derivative of this with respect to t would be positive 24 25ths times e to the negative 6t, and then divided by, and then dx dt is the same dx dt from earlier, 25 e to the 5t. And then, of course, if I simplify this, now 24 25ths over 25, that'd be 24 over 25 squared, and 25 squared is 625. And then e to the negative 6t divided by e to the 5t would be e to the negative 11t. Right, and this is what they're asking for, right? This expression here would tell me the concavity of any point on this curve, the curve described by these parametric equations. This expression would tell me the concavity of any point. But again, I would need to know the value of t that would take me to that point, though. Right. That's all I want. Punch in that expression, depending on t, that would give me the concavity, the second derivative at any moment. So 24 625ths times e raised to the negative 6t. or sorry, negative 11t I had written, negative 11t. And this should be good. Great. Again, they take you through it here. Wonderful. All right, so now we're finding the first derivative. So I've already shown you this well times, right? You got to find the first derivative on your way to the second derivative. So find the first derivative of a parametric curve. And once again, they're giving me the parametric equations for some curve. And then they just want an expression, depending on t, depending on the parameter t, that would give me dy dx. That would give me y prime, the slope of the tangent line anywhere. So very similar start to as like the last couple examples. All right, so the way x depends on t, the x coordinate of any point I'm at depends on t is this way. It's negative 12 times the square root of t, which I'm going to write this way. Negative 12 times t to the half power, right, for the power rule when I do derivatives. And then y of t, right, y depends on t this way. It's negative 8 times the square root of 8t plus 9, which once again with the roots, I'm going to write this way as negative 8 times the quantity 8t plus 9 to the half. And they say that, t must be positive here, non-negative here, so that way we're not taking square roots of negatives and getting imaginary x coordinates and imaginary y coordinates, right? All right, pardon me with all the sniffling. All right, so all they want is that first derivative, right? dy dx, y prime. Once again, first derivative of y with respect to x. If we have parametric equations, we can find that, dy dt for the numerator, and then dx dt, right? The derivative of x with respect to t in the denominator. All right. So applying the power rule also with the chain rule here, half of negative 8 is negative 4, but then I'm going to be multiplying by 8 later with the chain rule. So it'll be negative 4 times 8, negative 32, and then times 8t plus 9 to the negative half. And that'd be the dy dt divided by, and then dx dt would be, negative 6 times t to the negative half, right? Negative 6 times t to the negative half. And honestly, this is good. But if you want to rewrite it, negative 32 over negative 6, that'd be a, 16 of positive 16 thirds. And then I could flip these, make this t to the positive half in the numerator, and then 8t plus 9 to the half in the denominator. And both of these are to the half, so this is just like one big square root. So if you want to keep writing it with roots like they had initially, this would be 16 thirds times the square root of t over 8t plus 9. And I'll type this. That expression would give me the slope of the tangent line to any point on the curve described by these equations. But again, I would need to know the value of t to find dy dx, to find the slope of the tangent line. Yeah, so we're just entering this expression depending on t here. 16 thirds times, and then got the square root here of a fraction. And inside that square root is t over 8t plus 9. And this should be good. Great. All right, so they wrote it with the square root separate, but whatever. It's equivalent. All right, moving on. All right, so another one where we're asked to find the first derivative and write an expression, depending on t, the value of t at the point that you're at. All right, so this is just like the other ones, right? So far, all these examples have started off pretty similarly. All right, so the x coordinate of whatever point I'm at is 9 times the sine of 6 times the value of t, right? The value of my parameter t. Then y of t is -8 times the cosine of 6t. Right, and they just want an expression for the first derivative, right? dy dx, y prime. Right, and again, I'll keep writing this. This is the derivative of y with respect to t divided by the derivative of x with respect to t. All right, so the numerator here is, the derivative of y with respect to t. So that's this here, right? The derivative of this, which would be -8 times negative sine of 6t times 6, right? Chain rule. So this would be positive 48 sine of 6t. There's the derivative of y with respect to t. And then the denominator is the derivative of x with respect to t. Here is x in terms of t. The derivative of x would be 9 times the cosine of 6t times 6, right? So times 54 cosine of 6t. But then if we simplify this, again, this is 8 times 6, this is 9 times 6. So this reduces to 8/9, right? 8/9, and then sine over cosine of something is tangent of that thing. So tangent of 6t. And here we go. That's all they want, right? Give me an expression depending on t, so that I can use that expression to find the derivative, the first derivative, dy dx y prime of the curve, described by this. And this would once again be one of those ellipses. All right, but that's all. This is all they want. Right, so dy dx is 8/9 times the tangent of 6t. And that should be good. Great. All right, so now you saw a couple examples now, and actually in all 4 of the examples I've done so far, 4 or 5, I've been finding this first derivative expression. Well, now we're actually going to be using it to find the slope of the tangent line and the equation for the tangent line to some parametrically defined curve. So here, determine the slope. All right, so we're not asked for the equation here, we're just asked for the slope. So I just need to plug in this t equals 1 to my first derivative expression, right, to find the slope of the tangent line. So determine the slope of the tangent line at t equals 1 to the curve defined parametrically by these equations. Enter your answer as an exact answer, right? So no calculators, no rounding. Right? Right, so here's the equation given. X of t is -4 times the square root of 7t, which, again, I'm going to write this as -4 times 7t to the half power. And then y of t is 7 times the square root of 7t plus 4, which once again I'll write this way to make the derivative easier to do. 7 times the quantity, 7t plus 4 to the half. And they are mentioning that t has to be greater than or equal to 0 here. All right, so they're asking us find, dy dx. Find the slope of the tangent line when t equals 1. Right, so at the point when t equals 1. So watch this, right? So I'll go to the curve. Now let's go back to Desmos here. I'll enter this curve just to see what it looks like. All right. So parentheses, the x was -4 times the square root of 7t, comma, y was 7 times the square root of 7t plus 4. Right. Now this was start at 0, 14, so it's starting way up here. Here it is. Right, here's the curve. And if I made it a little bigger here, t 0 to 10, huh? How about that? There's the curve. Now the point we want the tangent line at is, that point there, t equals 1. Right? I know you can barely see it, but this point right here, where t equals 1. Now, of course, I could go through here and just replace all the t's with 1, so that'd be 7 there, and then this would be 7 here, and there you go. I'll label it. There's the point when t equals 1. Now you can see zooming in that, the tangent line to this curve is going to have a negative slope. This is a negative slope tangent. So when I find the value of the derivative here, it should be negative. All right, it should be negative. Well, let's see. All right, so let's go. Remember, dy dx, once again, I'll keep writing this. You're doing the derivative of y with respect to t divided by the derivative of x with respect to t for these parametric curves. Now the derivative of y with respect to t, right? So the numerator is going to be the derivative of y. So that's going to be 7 halves times this to the negative half, but then times 7 again. So 49 halves times 7t plus 4 to the negative half. And then the denominator is dx dt, which will be negative 2 times 7t to the negative half, but then times 7 again. So negative 14. Right. Again, negative 2 times 7, right? Negative 14, and then times 7t to the negative half, right? Now 14 is, 2 times 7. 49 is 7 times 7. So the 49 over the 14 here will be 7 halves with another 2. So this is negative 7/4 times, and then I would flip these like earlier, and this would be the square root of 7t over 7t plus 4. All right, because we got negative powers, you can flip them, right? All right. Sorry, I'm sniffling a lot. All right. So this is the derivative anywhere on the curve. I just need to know the value of t at the point. And they tell us, when t equals 1. So dy dx here when t equals 1, well, that would just be 7 over 11 here. So it'd be negative 7/4, times the square root of 7/11. And this is what I'm going to type in. But that would be a negative number. We saw back on the graph that at this point, this is the x coordinate, y coordinate, negative 10 something, 23 something. At that point, tangent line should have a slope of negative 7/4 times the square root of 7/11, right? Some negative number. So that's what I'm putting in here. Now they have m equals, right? M for slope usually. And I'm putting negative, 7/4 times the square root. And then inside that square root, 7/11. Great. All right, so they rationalized it, multiply the top and bottom here by the square root of 11. Whatever, we got the same value. All right. All right, so same deal, but this time, not only do they want the slope, all right, but they want the equation of the tangent line. All right, they want the equation of the tangent line. So not only will I need the slope of the tangent line, but I'll also need to know the point on the curve that we're going through. Remember to write the equation of a line. You need point and slope. Oh, I'm so sorry about my sniffles. Stop pointing them out. All right, so here was our curve. All right, and I'll go to Desmos too. When we get the equation of the tangent line, I'm going to graph the curve, graph the tangent line. You'll see that it's tangent. So x of t is negative 3 times the sine of 4t. And y of t is given as 7 times the cosine of 4t. Right, so another ellipse, right? We saw this in the very first example, another one that's going to be an ellipse. Now, at t equals, the value of t they're giving us here is pi over 3. X of pi over 3, the x coordinate that we're at. Now this would be negative 3 times the sine of 4 pi over 3. Now the sine of 4 pi over 3 would be negative square root of 3 over 2. So this is positive 3 root 3 over 2. All right, negative 3 times negative square root of 3 over 2. So that's the x coordinate that we're at. And then the value of y at pi over 3 would be 7 times the cosine of 4 pi over 3. Now the cosine of 4 pi over 3 is negative half. All right, so the y coordinate is negative 7 halves. All right, so the point on the curve and the point that our tangent line is going to run through has these coordinates, right? 3 root 3 over 2, comma, negative 7 halves. All right, and we'll see that on the Desmos calculator. So that's part of it. That's going to help us determine the line. Now I want the slope. All right, we want the slope of the tangent line, which is, dy dx, which once again, I'm going to do dy dt divided by dx dt. Okay, so dy dt is negative 28 sine of 4t divided by, and then dx dt is negative 12 cosine 4t, which after simplifying would be positive, right? That's 4 times 7, 4 times 3, positive 7/3 tangent of 4t. Right. Now at, this point at t equals pi over 3, dy dx here would be 7/3 times the tangent of 4 pi over 3. All right. Well, we know that the sine of 4 pi over 3 is negative root 3 over 2. The cosine of 4 pi over 3 is, negative half. So this would be positive square root of 3. So this would be 7 times the square root of 3 over 3. That's the slope. All right, so I have a point. I have a slope now. So the equation of the tangent line, I can start off writing it. All right, so the tangent line, I can start off writing it in point slope form. So there's my point. There's my slope. So y, remember changing y plus 7 halves, right? Y minus negative 7 halves equals the slope, 7 root 3 over 3, times the quantity, and then change in x, x minus 3 root 3 over 2. And honestly, it didn't say put it in slope-intercept form. It just said solve for y. So I'm going to write this out and then minus 7 halves. So we have y equals, our slope, 7 root 3 over 3, times x minus 3 root 3 over 2, and then minus 7 halves. And this is what I'm going to type in here. Now let's go to the calculator. All right, I'll go to Desmos and we'll verify this. All right. All right, so back to the Desmos and get rid of this stuff. All right, so again, this should be some ellipse. You'll see, right? I got parentheses, x was negative 3 sine of 4t, comma. Y is 7 cosine of 4t. And I'll just go 0 to. Now, if there's sine of 4t and cosine of 4t, right, those would both have periods of pi over 2. Right, so that 0 to pi over 2 for t should give me the whole ellipse as you're seeing here. Now, again, I'm just going to copy that, and just replace t with pi over 3. And they wanted pi over 3. So replacing the t's with pi over 3 gives me this point. All right. So you see this point here with x coordinate about 2.5 and y coordinate negative 3.5. I'm going to draw the tangent line that we had. I said the tangent line would be this. Y equals, let me actually look at my paper. So the slope was 7 square root of 3 over 3 times the quantity, x minus, and then 3 square root of 3, SQRT, square root of 3 over 2, and then after that, minus 7 halves. And you see, I'll make it like a dotted line or a dashed line here. And you see that that line is definitely tangent to the curve at this point. Right? It's touching that curve at just that single point there. Right? So tangent to the ellipse at that point. So this is a correct line. And that's what I'll type here. So we had 7 times the square root of 3, and it says right exact answers, right? So you got no calculator, no rounding, right? So 7 root 3 over 3 times the quantity x minus, and then we had 3 square root of 3 over 2, and then minus 7 halves. They probably put it in slope-intercept form, but this should be good. Yeah, they put it in slope-intercept form, but whatever. Right? Same line. Yeah, so remember, for any tangent line, any line at all, you need a point and need the slope. All right, the slope, which will be the first derivative. So you plug in the value of t first for the point, then you find the derivative, and then plug in the value of t again for the slope, and then you can write your equation. All right. All right, so we're back to just finding the first derivative. So here, find the slope of the line defined by the parametric equations without eliminating the parameter. Now, these are both just straight up linear equations. This is kind of a silly one. You see how x equals -4 and it doesn't depend on t at all? So that means no matter what t is, x will be -4. So that's a vertical line. This is describing a vertical line. I'll show you. Let's go here. Put in those parametric equations they gave us as an ordered pair. So the value of x is -4, and then the value of y, depending on t, was, -2 minus 2t. And you see how no matter what t is here, it goes 0 to 10, -10 to 10, whatever, the value of x is always -4. We get a vertical line. So this is good. No matter where you're at, you have a vertical line. And remember, vertical lines have undefined slope, or I guess you could say infinite slope, but the slope is undefined. So back here, they said if the slope is undefined, enter this, circle with the slash through it, this empty set symbol. So that's what I'm going to do here. Right, now if you were to do the dy dt over dx dt thing, right, dy dt is -2 divided by, and then x is a constant. So dx dt is 0. You got -2 divided by 0. And remember, dividing by 0 is undefined. So either way I look at it, I'm entering this empty set symbol. Let's see, -2 over 0. Bad. All right, so just like before, give me an expression for dy dx, right? How would I find the slope of the tangent line to this parametric curve at any value of t? All right, this one's simple enough, so I'm just going to say it out loud. Remember, we're doing dy dt over dx dt, but these are both linear. So dy dt is -2, dx dt is +2, and -2 divided by +2 is, -1. The slope of the curve that's described here is always going to be -1. Great. All right, so this is once again just what's an expression help me figure out the slope of the tangent line, right? dy dx, the first derivative for any given value of t. All right, so this one I'll actually write out because it's not just simple linear functions like the last example. So x of t is -3 times e to the -9t. Y of t is e to the 7t. All right, so again, dy dx, right? Y prime, the first derivative, slopes of the tangent lines. We're doing dy dt over and then dx dt. All right, so dy dt is 7e to the 7t divided by, and then dx dt would be 27 e to the -9t. And that would be 7/27 e to the 16t, right, if I simplify. There's your expression. That would help us calculate the first derivative, right, the slope of the tangent line at any point on this curve, as long as I knew the value of t. So 7/27 times e to the 16t power. Great. All right, so that one's done. This find the first derivative of a parametric curve. Once again, I'm only working through this heading on derivatives of parametric equations, so we just got the two left, the two sub-objectives left. All right, so back to determining the equation of a tangent line. Now, okay. This one's a little different. It says find all points on the curve defined by these equations. So here's our parametric equations that have a slope of 3, right? So with a tangent line that has a slope of 3. So we'll find our first derivative and then try to figure out where that's equal to 3. And what points are they talking about? What points on the curve would correspond to that? Right. And I'll show you on the graph too. We'll do a graph in Desmos and see these tangent lines with a slope of 3. All right, so we have x of t equals, t plus 1 over t, which is also t to the negative first, right? This would be t plus and then t to the -1. And then the y of t is t minus 1 over t. All right. So t minus t to the negative first. All right, so look at, we're doing, I'll write this all the time, dy dx, right? You do dy dt divided by dx dt. All right, so dy dt would be 1 and plus, 1 over t squared, right? T to the negative second. And then dx dt would be 1 minus t to the negative second, so 1 minus 1 over t squared. Now, if you write this as this is a complex fraction, right? If I multiply the top and bottom by t squared, the numerator would be t squared plus 1, and the denominator would be t squared minus 1 if you multiply the top and bottom by t squared. Okay. Now, we're trying to find when is this derivative, right? They said, where is the slope of the tangent line, the slope of the curve, dy dx, where is this equal to 3? Okay, so I'm taking this expression here, setting it equal to 3. We're going to find some values of t and then plug them into our coordinate expressions up here to find the points that they're talking about. And I'll go to the graph and show you. Now, if t squared plus 1 divided by t squared minus 1 equals 3, that means, t squared plus 1 must be equal to 3 t squared minus 3, right? Multiplying by t squared minus 1. This is a quadratic here. Take everything to the right, let's say. Subtract t squared, that's, 2t squared. Subtract 1, that'd be minus 4. I can divide by 2. Everything's got a factor of 2. So this would be 0 equals, t squared minus 2. So the solutions to this are when t equals, the square root of 2, or when t equals negative square root of 2. All right, so let's figure out what points they are here. All right. When t equals the square root of 2, x of the square root of 2, the x coordinate of our point would be, the square root of 2 plus, and then 1 over the square root of 2. Which, if I multiply the top and bottom here by square root of 2, this would be half the square root of 2. So this is 1.5 square roots of 2, 3 halves times the square root of 2 when you put them together. And then the y coordinate when t is the square root of 2 would be, t minus 1 over t, so square root of 2 minus 1 over the square root of 2. And again, this is just square root of 2 over 2, half the square root of 2. So 1 square root of 2 minus half square root of 2, that'd be half square root of 2. Right. So at point, 3 halves of the square root of 2 and 1/2 the square root of 2, dy dx is equal to 3. Right, and we can see the tangent line would be y equals, 3 times the change in x, so x minus 3 root 2 over 2. And then, y minus this, and I would add it, so plus root 2 over 2, right? This would be the tangent line at that point. And let's see that happening. So I'm going to go to the Desmos again. Now our parametric equations were t plus 1 over t, comma, t minus 1 over t. All right, so here was our curve. All right, now it's not the whole curve, right? I could go, now I want to go up to, one value is t is negative square root of 2, one value is t is positive square root of 2. So I'll go from just negative 2 to 2 here. And you'll see we're going to get parts of a hyperbola, it looks like. I'm going to copy this and just replace all the t's with square root of 2. All right, so here's a square root of 2, square root of 2, square root of 2, and replace the last t here with the square root of 2. So see we're at this point. All right, we're at this point here. I'll label it. It's got this x coordinate, this y coordinate. That's 1.5 square root of 2 and 1/2 square root of 2, right? The x and y coordinate I found earlier. And then you'll see that the slope of the tangent line is 3 there, right? When I put in y, y equals that line we had, 3 times x minus 3 square root of 2 over 2, and then plus square root of 2 over 2. See, it's tangent at that point. I'll make it dashed or something a different color and dashed. And you can see, zoom in here, this red dashed line is definitely tangent to that curve at that point. It's got a slope of 3. All right, so that's one answer. Okay, here's one of the answers. Because they asked for the points, where the point at what points is the slope 3. So there's one answer. But then, that was when t was positive square root of 2. The other answer is going to be when, t equals negative square root of 2. And when t equals negative square root of 2, right, you're pretty much just getting the opposite of these, right? The value of x at negative square root of 2, all right, that'd be, it's t plus 1 over t, so negative square root of 2, and then minus 1 over square root of 2. This would be negative 3 halves square root of 2 after rationalizing. And then the value of y at negative square root of 2 for t would be, t minus 1 over t. So negative root 2 plus 1 over root 2, right, minus a negative. And when you rationalize, this would be negative half square root of 2. So there's our point. So the other point, x coordinate, negative 1.5 times the square root of 2, and then y coordinate, negative half times the square root of 2. And this will be the other answer. And I'll just go to Desmos and show you, let's zoom out here. That's going to be this point down here, right? When I replace all these with negative root 2, so negative, 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 and negative, see that takes me down here. This is negative, right, this purple point. And all that would really change is this become in the line plot that becomes plus, and then this would become minus, right? You see the tangent line there with a slope of 3. So yeah, so our answers are these 2 points. These 2 points. The slope has a curve. The curve has a slope of 3. All right, so one of them was at 3 square root of 2 over 2. And then the y coordinate was square root of 2 over 2. And then just the opposites of these for the other one. So I'm just going to copy and paste them and put negatives in front of them. Come on. Copy, paste. All right, let's throw some minus signs in front of them. Those should be the points that have a slope of 3 on that curve. Right, a tangent line with a slope of 3. Great. All right. Okay, and then we're back to this is very, very similar to a problem we saw earlier. We got the parametric equations for another ellipse here, but they want, the equation of the tangent line for the point on this curve, when t equals pi over 3. The value of the parameter is pi over 3, and enter an exact answer. So again, no rounding, no calculators. All right, so this time I'm not going to go to Desmos. I'm just going to do it, on paper here, save some time. All right, so x is 3 times the sine of 5t. And y depends on the parameter t this way. It's negative 5 times the cosine of 5t. Now at, t equals pi over 3, all right, the value of x, the x coordinate of our point is 3 times the sine of 5 pi over 3, which is something we should know, right? Unit circle, trig function stuff, right? The sine of 5 pi over 3 is negative square root of 3 over 2. So this would be 3 times, negative 3 times root 3 over 2. All right. So there's the x coordinate of our point. And then y, I have to put pi over 3 here. Right. Then y at pi over 3 would be negative 5 times the cosine of 5 pi over 3. All right. Now the cosine of 5 pi over 3 is a half. Positive half. So this is negative 5 halves. Right, so there's our point, right, the x coordinate, y coordinate of the point on our curve. Now I want the slope, right, for the tangent line. That's the first derivative, dy dx, y prime. So once again, when we have these parametric equations, this is going to be calculated, dy dt over, and then dx dt. And then we'll plug in the value of, pi over 3 for t. Dy dt would be positive 5, well, positive 25 times the sine of 5t. All right, divided by, and then dx dt would be 15 cosine of 5t. And very similar to ones we've seen before. This will be some multiple of the tangent of 5t, right? This will be 5/3. 5/3 times the tangent of 5t, which, at pi over 3, the slope, right, I'll use m this time, the slope would be 5/3 times the tangent of 5 pi over 3. All right, now we know the sine of 5 pi over 3 is negative square root of 3 over 2. The cosine of 5 pi over 3 is a half. So the tangent is negative square root of 3, so this is negative 5 root 3 over 3. So there's the slope point. And so the equation of the line would be y minus, negative 5 halves. So y plus 5 halves equals the slope, negative 5 root 3 over 3 times the quantity, and then x minus the x coordinate of our point, which would be x plus 3 root 3 over 2. And then, of course, to get y alone like they want, I'm going to subtract 5 halves. So we'll do this, y equals this minus 5 halves. And this right here is what I'm going to type. That'll be our tangent line. So y equals negative 5 times the square root of 3 over 3 times the quantity x plus 3 square root of 3 over 2. And then minus 5 halves. That should be good. Again, they probably put it into slope-intercept form, distributed the slope here, but it should be good. Yeah. All right, so that objective's done. Again, I'm only going over this one heading here, the derivatives of parametric equations. So all that's left is what we started with, right? The first two problems were on this find the second derivative, right? The concavity, the concave up, concave down, concavity of a curve at any given moment. Yeah, so the rest of these should be concavity, second derivative. All right, so we find the first derivative, right? And then we find the first derivative of the first derivative, right, for the second derivative. So determine the concavity of the curve represented by the parametric equations here, when t equals 1. When t equals 1. So I'll show you on Desmos that it'll be concave up or concave down, or an inflection point, right? We'll see. We'll see. So here are the parametric equations. And x of t is negative 6 times e to the negative 2t. And then y of t is 5 times e to the negative 7t. Right? So again, first derivative, right, dy dx, doing the derivative of y with respect to t, divided by the derivative of x with respect to t. So derivative of y with respect to t would be negative 35 e to the negative 7t divided by, and then derivative of x with respect to t would be 12 e to the negative 2t, and simplifying this, these don't have any common factors, so this would be negative 35 twelfths, and then e to the negative 5t. Okay, so that's y prime, all right? That's dy dx, y prime, first derivative. Now the second derivative, right, d squared y over dx squared, right, and d2y over dx2. Remember, the second derivative of y with respect to x is the first derivative of y prime with respect to x. And I calculate this the same way I did the first derivative of y. You're doing the derivative of y prime with respect to t in the numerator divided by the derivative of x with respect to t in the denominator. Here's y prime. All right, so the derivative of this with respect to t would be, let's see, 5 times 35, 150 plus 25, 175 over 12, positive, right? So it would be 175 twelfths times e to the negative 5t. Right? There's the derivative of y prime with respect to t in the numerator. And then this derivative of x with respect to t is the same as before. That's down here, 12 e to the negative 2t. And after simplifying, this will be 175 over 144, right, 12, 12, and then e to the negative 3t. So there's the value of the second derivative at, any point. You just need to know the value of t. And then at t equals 1, this would be I'll just say y double prime equals, and again, this is y double prime, would be equal to, now, if t equals 1, this is e to the negative 3, which is 1 over e cubed. So this would be 175 over 144 e cubed, which is positive. This is a positive number. So the curve is concave up at that point. Concave up, right, doing something like that. All right, well, let's actually see that happening in the graph. Right. So back to Desmos here. Let's get rid of the old problem stuff. Right, so I'm going to put in my parametric equations, right? X was negative 6 times e to the negative 2t, comma. Y was 5 times e to the negative 7t. And because we're plugging in t equals 1, I'm going to go 0 to 2 here just so we get 1 in the middle. All right, when t equals 1. All right, so again, let me copy this and plot that point. So just replace t with 1, that makes that negative 2, and that makes that negative 7, right? Let me label that. So not in the middle, but here it is. So I'm at this point when t is 1. And you see how the curve is concave up, right? It's definitely it looks like it's a concave up curve for sure, up to this point especially. This is a concave up at that point. Now it would have a negative slope, right? If you did the first derivative here, you'd get a negative value. But when the second derivative, you get a positive value because it's concave up, right? So it's clearly concave up, right? Now, of course, I could have just done all that and said concave up here, right? Because they didn't ask for a value here. So I could have gone to the calculator and did this and looked at what happened when t was 1 and said concave up, but still, I wanted to do the calculations as well, all right? Because that's going to be important. All right, so yeah, they do all the calculations, right? Got the same thing I got there, which is positive. Cool. Some more second derivatives. All right, now remember inflection points from, like, first calculus 1. An inflection point is where a curve changes from concave down to concave up, or from concave up to concave down. And at an inflection point, the second derivative will be 0 and go from positive to negative or negative to positive around that. So they're asking us here, which statement is true about the inflection point on the curve represented by these parametric equations? All right, so I'll find the expression for the second derivative. Again, x of t. And we have these exponentials with base e, so this will be pretty similar to the last problem. Negative 5 times, e to the 2t, and y of t is 6 e to the t. Now, if I'm doing, dy dx, first derivative, I'm going to go to the second eventually. Remember, this is dy dt over dx dt. Now, dy dt would be 6 e to the t. Dx dt would be negative 10 e to the 2t. And dividing these gives me negative, That's 2 times 3, 2 times 5, negative 3/5 e to the negative t. So there's y prime in terms of t. And then the second derivative for concavity, find inflection points, and I'm doing the first derivative of y prime with respect to x. So just like the first derivative of y, I'm doing the derivative of y prime with respect to t up in the numerator and dividing by the derivative of x with respect to t in the denominator. Now this was y prime. So the derivative of this with respect to t would be positive 3/5 times e to the negative t divided by, and then derivative of x we saw earlier was negative 10 e to the 2t. And when I divide these, this would be, negative 3/50. All right, put the 10 with the 5 here. Negative 3/50 times e to the negative 3t, which would be over e to the 3t. This is negative for any value of t, right? Because exponentials, remember, e to the 3t is always positive, but then your times is negative 3/50 here. So there aren't any inflection points, right? This'll always be negative, this second derivative. So that means the curve has no inflection points. There's no point where it goes from negative to positive, the second derivative, or where the second derivative goes from positive to negative. There are no points, there are no values of t where this second derivative is 0. So there are no inflection points on this graph. Right? And you can see that would be an exponential. And also, it's always concave down. Right? This second derivative expression here would always be negative. So the curve would always be concave down. Right, you can see that. I'll go to the picture. Again, very similar. X was negative 5 e to the positive 2t, and y was 6 e to the t. If you see here, that would start off when t equals 0. You'd be at the point negative 5, negative 6. So let me bounce this out a bit. There it is, negative 5, 6. Sorry, right up here. And you see, even for just t equals 0 to 2 here, it's concave down. Right, definitely curling downward. Right, but obviously it's always going to be concave down this. No inflection points. There is not an inflection point, is what I'm answering here. So again, they take you through the derivation of the second derivative expression and say, hey, this is always negative. Look, it's concave down all the time, that kind of crap. All right, now this time, they just want the expression for the second derivative in terms of t. So like I've been doing. All right, so once again, we have our parametric equations, right? X sub t is negative 3t squared minus 3t plus 7. And then y of t is negative 9t cubed plus 6t squared plus 9t minus 3. So a couple of polynomial equations. So again, the first derivative, y prime, dy dx. I'm doing the same thing every time here. Got dy dt in the numerator, divided by, and then dx dt in the denominator. Now the derivative of y with respect to t, the power rule here would be negative 27 t squared plus 12t plus 9, all right, divided by, and then dx dt would be negative 6t minus 3. Now I can see a little way to simplify this a tad. All these have a factor of 3, all these coefficients, and in fact, I'll pull out a negative 3 from them. So if I just multiply the top and bottom by negative 1/3, multiply the top and bottom by negative 1/3, that'll give me 9t squared minus 4t and then minus 3. All right. And then dividing all these by negative 3 gives me 2t plus 1. All right, 2t plus 1. There's y prime. Y prime in terms of t. Now, for the second derivative, right, again, you've been seeing this, the second derivative, d squared y over dx squared, remember, I'm thinking of that as the first derivative of y prime with respect to x. And then doing the derivative of y prime with respect to t divided by the derivative of x with respect to t. So this one's going to be a little annoying because, y prime up here is a fraction, a quotient. I got to use the quotient rule. So for this numerator part, all right, I'm going to take this to another page. Dy prime with respect to t here, remember it's a quotient rule. So denominator, 2t plus 1 times the derivative of the numerator, which would be 18t minus 4. And then minus, the numerator, 9t squared minus 4t minus 3 times the derivative of the denominator is just 2. And then all that divided by the denominator squared. And let's simplify the numerator a tad. Well, I see a factor of 2 in this product here. This is the same thing as 2 times 9t minus 2. So factor a 2 here. So I can factor a 2 out, and then I'd have 2t plus 1 times 9t minus 2 left over here, and then just minus, now I'll distribute the negative here. We got minus 9t squared plus 4t plus 3. And all that, divided by the quantity 2t plus 1 squared. And then if I multiply these two, you're getting 18t squared. All right, and then minus 4t plus 9t would be plus 5t, and then minus 2, and then putting stuff together up here, we get this. So 2 times, and then 18t squared minus 9t squared would be 9t squared. 5t, and then plus 4t would be plus 9t, and then negative 2 plus 3 would be plus 1. All right, and this is divided by, 2t plus 1 squared. That's dy prime dt. All right, and then we're dividing this by dx dt, which we already saw was this, negative 6t minus 3 dx dt. So, let's say, so the second derivative of y with respect to x, right, is this divided by, and then, down here I have dx dt, which was the negative 6t minus 3, which if you factor out negative 3, is negative 3 times 2t plus 1, and that'll make this a 2t plus 1 cubed, right? You'd have those two in the denominator. And then we have, negative 2/3. So negative 2/3, 2 over negative 3 times, and then your numerator, 9t squared plus 9t plus 1. And then down here, 2t plus 1 cubed. And this is what I'm going to type in. That was a hairy one because of the quotient rule. All right, so in the numerator, I've got, negative 2 times the quantity 9t squared plus 9t plus 1 divided by, and then denominator has 3 times the quantity 2t plus 1 cubed. 2t plus 1 to the third power. That should be the good expression for the second derivative. Great. Now they actually multiplied the whole thing out. I didn't do that, but that's something equivalent though. And again, they take you through the entire procedure again here. All right. Now, as I mentioned, right, I'm only going through these 3 objectives. So I am done with this video, right, on the derivatives of parametric equations. Part 2 will be on the other three with the integrals involving parametric equations heading, right? This heading here. So be on the lookout for that. I'll post that up later. All right, so as I say at the top of the video, right, remember that in these preview assignments, the questions I see may not be exactly the same as the questions you see when you work on the assignment yourself, but the objectives are the same. So I'm hoping that watching me do these here helps you in some way when you work on them on your own. All right, and thank you very much for watching.